Section 4.6, Satellites, fast-moving projectiles. When you have a slow-moving projectile, in the last section we said that the curvature of the Earth doesn't play a role. If the projectile is moving faster, though, it can matter. The Earth itself is curved in such a way that it drops about 5 meters for every 8,000 meters tangent to the surface, which means that you can look forward and you can see maybe if the world is, if everything in front of you is completely cleared out, no trees, no anything, you can maybe see about 8 kilometers, it's about 4 miles in front of you, before the Earth is curved away enough, 5 meters, where you can't see below it. So if you're standing on a cliff that's 5 meters high, if you throw this projectile, it's going to fall to the ground in 1 second. It takes 1 second for an object to fall 5 meters. Now, if we get to going throwing this thing fast enough, and that object can somehow travel 8,000 meters in a second, then it's not going to appear to fall. The Earth is going to move out from under it. The curvature of the Earth will move out from under it. So as the object falls, the Earth itself falls with it. Right? It moves away with it. And so what you have is that the object will essentially fall around the surface of the Earth. And any object that falls around the Earth, instead of falling into the Earth, we call that thing a satellite. If you try to do this at home, right, which is essentially to say launch something at about 8 kilometers per second, which is about 18,000 miles per hour. So you can try to do it on the surface of the Earth and launch something at 18,000 miles per hour. What you'll find is that the air resistance is going to immediately burn the thing up, even if you had a way to launch it at 18,000 miles per hour. There's just no way you could throw a baseball and have it go all the way around the Earth. A, you could never throw anything that fast, but also the air on the surface of the Earth would literally just destroy it as soon as it got to moving that fast. The air resistance would heat it so much it would incinerate essentially. So we can't launch satellites from the surface of the Earth, so we take them up into low Earth orbit or further, and we launch them from there. If we launch them from there, much less air resistance, we can get the things going at about 18,000 miles per hour, or a little less, and that will allow it to fall around the Earth. I say a little less because the further you move from the surface of the Earth, the slower you can go, and still make it so that the Earth falls out from under you. Okay, so if we do it on the surface, it got to be 8 kilometers per second. Do it just, at the tip of Earth's atmosphere, maybe you can go a little bit slower because you've got a little more space for the thing to fall over time. But in general, you want to hit at least 8 kilometers per second to get that object to go all the way around the Earth. Now, here's again where people start messing things all up. Satellites, especially when you see people in the International Space Station, are thought to somehow be free of gravity. And that's why people in the space station float. But this is not at all the case. Without gravity, those satellites wouldn't even stay in orbit around the Earth. Gravity has to exist where those satellites are, or else satellites just float out into space, the same way that Earth would float out into space if there were no gravity, holding it to the sun. In fact, the amount of gravity, or the gravitational force that you would experience at, say, the height of the International Space Station is almost exactly the same as it is on the Earth's surface. It's a little less because you're further from the Earth. Remember that inverse square law, the further away you get, the force drops by 1 over the distance squared, but it doesn't go to 0. And you're not that far away. So people tend to mistake this idea of astronauts looking weightless and floating around as being that there is no gravity, and that is completely wrong. Gravity has to exist in those places for those astronauts to be experiencing those things. If there's no gravity in space, how does the moon not just wander off? There has to be gravity that holds the moon to the Earth, the same way that holds the Earth to the sun. So saying there's no gravity and that's why they float does not make any sense. And the true portion of it is what we talked about in section 4.3. The space station and the person are falling around the Earth. The space station, the International Space Station, travels fast enough that as it moves forward, the Earth falls out from under it. Similarly, the moon and other satellites have to have some significant tangential velocity, right? So a velocity essentially parallel to the Earth's surface, as we saw in those other pictures, so that they can move fast enough so that the Earth will fall out from under them as the object is falling. Hey, technically, the moon is falling to the Earth, but it's far enough away and traveling fast enough that as it falls, it moves around the curvature of the Earth. So when we talk about an object moving around another object, or a satellite moving around another object, we refer to that path that that object takes as the orbit of the satellite, or the orbit of the moon. Technically, just like the moon is in orbit around the Earth is in orbit around the sun. And the Earth is essentially falling around the sun the same way. The Earth moves fast enough around the sun that it's not pulled into it. If the Earth suddenly froze in place and stopped moving around the sun, it would crash into the sun. Same thing with the moon. If the moon just suddenly stopped moving around the Earth, it would crash into the Earth. Gravity would then pull it down. But because it's moving fast enough, essentially sideways, then the Earth and the object fall away together, and the space between them never changes.